Hello, this is John Miyares, and this lesson, I promise you, is going to be much shorter than the last one. In the last section, we did some computations involving vectors that involved mostly addition and subtraction of their components. Here, we're going to begin discussing the idea of multiplying two vectors together. There are two common ways that one can consider multiplying two vectors together by. They are the dot product, which is also called the scalar product, and that's what we're going to be focusing on this lesson, and the cross product, or the vector product, which we are not going to be exploring at all in this course. On the whole, dot products are pretty simple to compute, but the most confusing thing to realize is that the final answer after taking the dot product between two vectors will be a scalar. And when I say a scalar, you may remember, we're just talking about that as a plain old number. Suppose u and v are written in component form as shown here, with inside the angle brackets u1, u2, and vector v will be v1, v2 inside the angle brackets. The dot product of u and v will be the product of the horizontal components, u1 and v1, plus the product of the vertical components, u2 and v2. As I noted before, the answer to the dot product will be a number, or a scalar, not a vector. One thing we can use the dot product for is to compute the angle between two vectors. Now, the formula that's provided here is not intuitive, but what we could say is that if theta is an angle between two vectors, u and v, in standard position, then the dot product of u and v can be computed as the length of u times the length of v multiplied by the cosine of that angle theta between the two vectors. Rearranging this formula will give us that the cosine of theta will equal the dot product of u and v divided by the length of u and the length of v. Taking this further will give us that theta will be the inverse cosine of that expression, the dot product of u and v divided by the length of u and the length of v. This might make more sense if we look at it in an example. Suppose we're asked to find the dot product and the angle between two given vectors, and those vectors are going to be u equals 5, negative 2 inside the angle brackets, and v equals 3, negative 4 inside those angle brackets. We could have also written these vectors as u equals 5i minus 2j, or v equals 3i minus 4j. Here are the formulas for the dot product between two vectors and the formula that can connect those dot products to the angle between the two vectors. The dot product will be the product of the two horizontal components, 5 times 3, plus the product of the two vertical components, negative 2 times 4. Multiplying this out and simplifying the results gives us 5 times 3 is 15, negative 2 times negative 4 is positive 8, which will add up to 23. Next, we want to find the angle between the two vectors, which means that if I was to draw these two vectors in standard position like they're shown here with the 5i minus 2j in red and the 3i minus 4j in dark blue, what I'm interested in is that angle theta that is between these two vectors right here. Now, while there's multiple ways that we could compute the angle measure, what we're going to do is try to use this formula that takes the dot product of the two vectors, then divides that product by the length of u and the length of v. The length of u can be computed using the distance formula to be the square root of 29, while the length of v can be computed also using the distance formula as the square root of 25, or 5. Putting this all together will get us to having theta equaling the inverse cosine of the quantity u dot v, which is 23, divided by the square root of 29 times 5. Plugging that into the calculator gives us a measure of theta equals 31.33 degrees. Why don't you try this one on your own? Same question. Find the dot product and the angle between these two vectors, u equals 3i plus 2j and v equals negative 4i plus 5j. Your formulas for the dot product and for computing the angle between the two vectors are given here. Go ahead and pause this video to give this one a try. So the dot product of u and v will be the product of the horizontal components, which are the coefficients of the i's, the 3 times the negative 4, plus the product of the two vertical components, which will be the coefficients of the j's, 2 times 5. Simplifying this will give us negative 12 plus 10, which is negative 2. Now we need to find the angle between these two vectors. If I draw out these vectors, what I see is that 3i plus 2j is in quadrant 1, while negative 4i plus 5j is in quadrant 2. It looks like the angle between these two vectors is about 90 degrees, and if it's not 90 degrees, then it's pretty close to 90 degrees. Let's run this through the calculator and see what this looks like. The length of u will be the square root of 3 squared plus 2 squared, which simplifies to the square root of 13, while the length of v will be the square root of negative 4 squared plus 5 squared, which will simplify to the square root of 41. Theta will then be the inverse cosine of the dot product, which was negative 2, divided by the product of the lengths of these two vectors, square root of 13 and square root of 41. Punching that into the calculator will give us that angle theta measures 94.97 degrees, which again, looking at our picture, seems fairly reasonable. Now we're going to introduce a new vocabulary word. Two vectors are said to be orthogonal, which is a fancy word that basically means perpendicular, if their dot product is 0. Now, at first glance, this may not seem reasonable, but let's look at this more closely. Angle theta is computed by taking the inverse cosine of the dot product of two vectors and dividing that by the length of vector u and vector v. If the dot product between vector u and vector v is 0, then what you're taking is the inverse cosine of 0, regardless as to what the lengths of u and v are. And the inverse cosine of 0 is 90 degrees, or pi over 2 radians. So ultimately, if we're given a problem where we are asked to determine if two vectors will be orthogonal or perpendicular, all we will have to do is take their dot product to see if the dot product equals 0. So let's look at an example. Suppose my two vectors are given here as 6 comma negative 3 in the angle brackets for vector u and 2 comma 4 inside angle brackets for vector v. So we could also say u equals 6i minus 3j and v equals 2i plus 4j. Taking the dot product, I'm going to multiply the horizontal components together, 6 times 2, and add that to the product of the vertical components, -3 times 4. That's going to give me 12 plus -12, which is 0. So in theory, these two vectors will be perpendicular to each other. So if I were to graph them, you would see that they should meet at right angles. Let's look at another one. Perhaps you can try this one on your own. Let's suppose that vector u equals 2i minus 8j and vector v equals -12i minus 3j. Pause this video and see if you can do this one on your own. This time, I want to draw a picture first. When I put these together, it looks like these two vectors form a right angle, and if they don't, again, it's really close. So let's run this through the dot product formula and see what happens. The dot product in u and v is going to become 2 times -12 plus -8 times -3. Doing the computations here makes this -24 plus 24, which will add up to 0, which would confirm that yes, in fact, these two vectors will be perpendicular or orthogonal to each other. One of the applications of dot products that are introduced in this section is the idea of something called work. From physics, the work W done by a force vector F in moving along a distance vector D is calculated by the formula W equals the dot product of force vector F and distance vector D. When they first introduce the concept of work in physics, they start by talking about it as force times distance, where they measure the force in newtons and the distance in meters. So the work unit is newtons times meters, which for that they created a special unit called joules. Sometimes you will see this measured where the distance is in feet and the force is in pounds to get a completely unspecial unit called foot-pounds. For this process, we're going to be looking at not just force multiplied by distance, but what we're going to do is consider that force and distance can be measured as vectors, and consequently, the work computed will be the dot product between the two vectors. Let's take, for example, what would happen if we were given a force F represented by the vector 2, 4 inside of angle brackets, which is moving an object from the coordinates 1, 2 to the coordinates 5, 4. And we want to compute the amount of work that it takes to move that object from one point to the other. Now, granted, where this gets complicated from a physics point of view is that I'm trying to move this object right 4 and up 2, but the force that is acting on this object wants it to go over 2 and up 4. So it is certainly not the most efficient way from getting from one point to the other. But we can still do the computation and see how this is going to work. The force vector is going to be 2, 4 inside the angle brackets. The distance vector can be computed by looking at the change in x and the change in y. 5 minus 1 is 4, and 4 minus 2 is 2. Computing the work as the dot product of the force and the distance will take 2 times 4 plus 4 times 2 to get 8 plus 8, which is 16. And that's all there is to this problem. Let's look at a slightly more complex example. A car drives 500 feet on a road that is inclined 12 degrees to the horizontal. If the car weighs 2,500 pounds, find the work done by the car to overcome gravity. This might make more sense if we draw a picture of it first. This is a picture of the car on the hillside. The car weighs 2,500 pounds, which is going to be this vector pulling the car downward that we're going to call negative 2,500j. That is going to be my force vector F because the force that is acting on the car is gravity, and gravity pulls things straight downward. The car is trying to move 500 feet up the hillside, which is going to be represented by this smaller red arrow underneath the car that's pointed up the hillside. That little vector is going to be my vector D. Looking closely at vector D, we're going to have to break down the vector into its horizontal and vertical components. If I was to try to draw a tiny reference triangle underneath the car, that red diagonal vector here, which we're going to call D, will have a magnitude of 500 feet along the diagonal, but we're going to break it down through its horizontal components. Horizontally, the car is going to travel 500 times the cosine of 12 degrees, and vertically, it's traveling 500 times the sine of 12 degrees upward. Decimalizing that result gives us D equals 489.074I plus 103.956J. Now let's look at the dot product of the force and the distance vectors to compute the work done to move this car up the side of the hill. Multiplying the horizontal components by each other and the vertical components by each other leaves you with 0 times 489.074 plus 2,500 times 103.956, which when we run that through a calculator and simplify it, we'll get 259,889.6 foot-pounds. Now, you might be wondering why it should make sense that the horizontal component of work falls out here, since you should think that there should be some work and some forces that are moving this car horizontally as well as vertically. Again, there are those forces at work that are coming from the engine, but we're not asked about that. In this problem, we are only asked about the work that is necessary to overcome the force of gravity. And since gravity is a vertical force, everything that we're doing is dealing with the work necessary to essentially elevate the car up the hill 103.956 feet. Here's one more example. JD pushes a lawnmower with a force of 50 pounds at an angle of 55 degrees with the horizontal. Determine how much work is needed to push the lawnmower across a 200-foot yard. Drawing a picture, here we have our guy JD who is pushing the lawnmower. This diagram should pretty much explain the behavior of the forces. The lawnmower is traveling horizontally along the ground, but JD is holding the lawnmower at an angle because he's pushing it down along the handlebars, which push on the lawnmower down here. So the gravity, the wheels, and the fact that it's flat is making the lawnmower move horizontally. Meanwhile, you would think that it would take less work to push this lawnmower horizontally than it would to push it at an angle. And that would be true. But in order to apply a force so that is horizontal and parallel to distance vector d, the handles would have to be on the ground. So you would have to be on the ground with it, getting rocks and grass chopped up and thrown backwards in your face as you push the lawnmower forward. Now, that wouldn't be very fun now, would it? Anyway, let's see what the math looks like here. The distance vector can be written as 200i plus 0j. The lawnmower is traveling 200 feet horizontally, but not going up or down a hillside or anything like that. The force vector has a magnitude of 50 pounds along a 55-degree angle with the horizontal. So what I'd want to do in order to take the dot product of the force vector with the distance vector is break down the force F into its horizontal and vertical components. This makes F equal to 50 times the cosine of 55 degrees times I plus 50 times the sine of 55 degrees times J. And again, looking at what I have for my reference angle here, the vertical component is going to be based on the sine opposite over hypotenuse, where my hypotenuse is 50 pounds, and the horizontal component is going to be the adjacent side of this reference triangle over the hypotenuse. That will be the cosine of the 55-degree angle times the 50. Decimalizing things gives us F equals 28.6788I plus 40.9576J. Now let's take the dot product of F and D. Multiplying the corresponding components together and adding them up gives us 200 times 28.6788 plus 0 times 40.9576 to get us 5,735.76 foot-pounds. Again, since the lawnmower is moving horizontally, all of the work is done through the horizontal component of the force vector. Even though JD is applying 50 pounds of force on the lawnmower itself, the fact that he's pushing it at an angle means that there's only a net force of about 28.6788 pounds that are actually heading in the horizontal direction. Put another way, if JD was to get on the ground and flatten the handlebars of this lawnmower, he would only need to push it at a force of 28.6788 pounds in order to accomplish the same amount of work that he would have had to get this at an angle of 50 pounds. So by doing it this way, it's not the most efficient way, but it is going to be probably the safest way. So that's all there is to this section. Hopefully that wasn't too painful. You really only have 3 formulas you're dealing with in this section. You have the dot product formula, where you're taking the products of the corresponding components and adding them to compute a dot product. The angle formula, where you're taking the inverse cosine of the dot product and dividing that by the length of each vector to get the angle between. And this idea of work, which is the dot product of force and distance. Here is some problems that you can try that will hopefully get you some confidence in working with these problems. As always, if you have any questions, you can either email me or post your questions on the discussion board for everyone to see. Thanks for watching, and we'll see you all soon.